start recording because apparently my lesson this morning is going to be too quiet. So let's do it again. All right, and we want to be on page 30, 30. Were there any questions from the homework? I don't know why I asked. I should just assume that you will ask me because you are adults in charge of your own lives and you can be like, hey, I didn't get whatever. Okay. All right. So, saturated and unsaturated solutions. 30. So if we have an unsaturated solution, it contains less than the maximum. Less than the maximum amount of dissolved solute. So that's what all this page is going to be about, is about unsaturated solutions. And this should actually say, if undissolved solute is present, in an unsaturated solution, then the system is not yet at equilibrium, and the rate of dissolving is going to be greater than the rate of precipitation or recrystallization. The words precipitation and recrystallization are meaning the same thing. Is good? Okay. Now, if we look at this particular solution is not yet full of solute particles. And what that means is that there will be more particles dissolving. So if we look at our red arrows or our dashed arrows on your page, because everything looks gray on your page, we have 1, 2, 3, 4, 5 particles dissolving, but only 1 particle recrystallizing. So what will be happening to our concentration here? The concentration will be increasing, right? Because we're dissolving more than we are recrystallizing. Yeah? So if we put some solute into the solvent, we put the solute into the solvent, in that moment that we put it in, let's draw a little rate graph here, rate. What is the rate of dissolving like if we just have thrown the solute into the solvent? What is the rate of dissolving like? Is it 0? Is it high? Is it low? If I've just thrown in the solute. No? I've got lots of solute.
But at the moment, nothing changes.
Okay, in the first millisecond, what's the rate like? From 0 to 1 millisecond. Is it high? Is it low? Is it medium? It's 0? So we have lots of reactant and no product. We have all reactant. Yes. Okay. At time 0, we have all reactant. So the forward rate is fast. So our rate of dissolving is high. Height, high. What can we say in that moment about the rate of recrystallization? How much product do we have? Yeah, we got no product yet. Therefore, our rate of recrystallization is 0. As time goes on, what is going to happen to those two rates? They're going to equal each other. How are they going to get there? Steep, shallow, flat. Steep, shallow, flat. Steep, shallow, flat. Okay. And at that point right there, these should actually be overlapping, but you know, it's so hard to draw them overlapping. At that point there, we have reached equilibrium. And at that point there, what can we say about the solution? The solution is saturated.
So all solutions precipitate eventually achieve saturation?
Yes, as long as you have enough solid there to reach equilibrium, then yes. Okay, so as time goes on, this would sort of be on the way to equilibrium, right? Our forward rate is slowing down a little bit, and our reverse rate has become something, so we'd be kind of on our way. Now, as time goes on, we could either reach equilibrium, which would look like that graph that we just drew, or what happens if we run out of solid?
Unsaturated? Wait.
It's going to remain unsaturated, yeah, because we can't go forward. And if we're not saturated yet, it won't go backward. So what would our rates look like under those conditions? Let's try that. So our dissolving rate is going to decrease, and our recrystallization rate is going to increase. But here, we've run out of solute. run out of solid. What happens to our forward rate, the dissolving rate? It stops. What happens to our reverse rate? It stops. Okay? It's not that it completely stops, it's just that randomly every once in a while a particle or two will get together and then they'll come apart.
Oh, because we don't have that.
Because we don't have very much, so like it's not going to be enough to like be meaningful. It's essentially zero. Yeah? Yeah. And same thing with the forward rate. I mean, every time you get one recrystallizing, you'll have one coming apart again, but both of them are so close to zero as to make no difference. Yeah? Okay. Are you going to have to draw this graph? No, but you should be aware that if we run out of the solid, this solution will be unsaturated. But if we have enough solid, then these two rates are eventually going to be equal. And these guys here are going to be saturated now. So while we are on the way to equilibrium, let's just backtrack for a moment. If we are on the way to equilibrium, is this a saturated or an unsaturated solution? Have we dissolved as much as possible if we're on our way to equilibrium, but we've not yet reached equilibrium? It is unsaturated. Okay, so this is unsaturated. The forward rate is faster than the reverse rate. This is unsaturated because we ran out of solid. And then finally, we might reach that saturation point where we have the two rates are equal and we still had some solid left. Okay? So, here we have a saturated solution. And the one definition, so this is definition one, a solution that contains the maximum amount of dissolved solute. If undissolved solute is present, in a saturated solution, the system will be at equilibrium. It is possible to saturate a solution and then remove the solid so it's just barely saturated, but there's no equilibrium. But it's a weird condition because technically to be saturated, you should have that equilibrium happening, but you could filter out that solid and be like, close enough, saturated. Because if I put in anything more, it wouldn't dissolve. Yes?
So like really like salt. The different chemical species have different saturation points basically. Like salt, I think you have to put like a lot of salt in water.
Yes.
To make sure it's saturated.
Yes. And we call that different amount that it takes to get to saturation. We call that the solubility. Okay?
that just kind of on the nature of the reaction?
Yes. So for example, if we had sodium chloride, okay, which is Na plus, Cl minus, those are both third row elements. Okay, if we were to replace sodium with magnesium, which is also a third row element, but has a 2+ charge, and if we replace chlorine, third row, with sulfur, third row, so sulfur has a 2- charge, magnesium sulfide is going to be less soluble because the 2+ charge and the 2- charge attract each other more than the 1- charge and the 1+ charge. Yeah? So that's the nature of the reactants. Now, it's also going to depend on things like ion size, but, you know, if you're comparing things in the same row, the size of the ions are relatively similar. Yeah. Okay. So here you can see we have reached saturation. Take a look at the number of particles in solution. What can you say compared to our unsaturated solution? Here's unsaturated. Here's saturated. What can you say? Now there is... Here, can I make them so you can see both of them? There, now you can see both of them at the same time.
They're equal amount of arrows coming in.
I'm going to try something. Hang on. Okay. Now you can see them side by side. What can you say about the amount of solute in each of them? Where is the amount of solute dissolved greater? On the right-hand side, there's a lot more dissolved particles, yes? So we have reached saturation. It is full with ions now. Could you put any more ions in there? No. Okay, so we can write down here that this solution is full of ions. Yes, all the hotel rooms are booked. All the hotel rooms are full. So anytime, in order to get a guest to check in, to go into solution, 1, 2, 3, anytime the guests check into the solution, another guest has to check out of solution. 3, 2, 1. I don't know why I wrote 3, 2, 1. I could have written 1, 2, 3. That would have made more sense, but there we go. Yes? So the rate of dissolving is equal to the rate of recrystallization. And what's going to happen to our concentration here in this situation? Concentration stays the same. What if I added extra solid? What if we add extra solid to a saturated solution? Yeah, you just have more solid. Yes? Have you changed how much will dissolve? No. What has happened to the surface area? So let's say we started with saturated solution and we have a little pile of solid at the bottom. And then we add more solid. What has happened to the surface area if we added more solid? Surface area has increased, decreased, stay the same. Increased. So what has happened to the rate of dissolving? Does it increase, decrease, or stay the same? What happens to rate when you increase surface area? It increases. Because there's more area for the particles to dissolve off of. Yes? You can imagine if you had a single solid crystal down at the bottom, you couldn't get much dissolving happening, could you? But if you had a whole pile of them, you could get a lot more dissolving. What has happened to the rate of recrystallization? Has it stayed the same?
At equilibrium, rate of dissolving increase, and the rate of crystallization also has to increase.
Yes, it also has to increase. And if you think about it, where does recrystallization occur? It occurs at the surface. And if you have a bigger surface, you are going to have a faster rate of recrystallization. Okay, it also increases and by the same amount. So can you change the solubility, how much will dissolve by adding more solid? No. Can you make this equilibrium shift by adding more solid? Nope. Okay? You just end up with a bigger pile of solid and a faster forward and reverse rate. This is a question that I always like to ask and that everybody always gets wrong. Okay?
What is the test? Because AP exam.
Do you know what? Honestly, I'm going to put the test where I'm going to put it, but if you have an AP exam, and if you have schedule that doesn't work with that, we'll just give you a test on a different day. Okay? Because everybody's got different AP exams, different days. It's 2 weeks. Do you know what I mean? I can't be okay, we're going to put it off forever and ever, amen, and whatever. I think I'll just be I'll have 17 different versions. And I'll just be you get version A, you get version B, you get version, you know what I mean? I just think that'll make life easier.
Do you know when it's going to be?
No. No, we need to finish this. We need to finish 3.4, 3.3. And then you guys need to practice your KSP calculations because there's 5 different types. And the only thing that's hard about any of them is figuring out what type you are being asked about and using the correct tools. Yeah? So, in order to help you sort out those 5 different types, of solubility problems, we're going to be talking about the method of making the saturated solution. So one way to make a saturated solution, the easiest way, I call it dump and stir. What do? You take your solid and you dump it into water, and then you stir it. So this is salt AB, okay? Now, if you stir it and there's no solid, you're like, oh, it all dissolved. What would you have to do next? You have to dump in more and then stir it. And then what next if it all dissolved? More. And you stir it and oh my gosh. So you repeat this. Okay, so you dump and stir and repeat. So it's really dump, stir, and repeat. Until some solid remains. So dump, stir, and repeat until some solid remains. At that point, you have hit the maximum concentration. You have a saturated solution. And your ions, where did your ions come from? They came from this compound, yes? What's the ratio of A to B in that compound? 1 to 1. Your ions will be present proportional to the coefficients. For every one A, you will have one B, because A came from AB and B came from AB. So for example, so in dump and stir, you will have one compound. Okay, so for example, our one compound in this case is CaF2. So we would take some CaF2 solid, we would dump it and stir. And because it's dump and stir, the ions are proportional to the coefficients. So if our concentration of calcium fluoride, SAT, what does that SAT stand for? Saturated, is 2 times 10 to the negative 4 molar, what is the concentration of calcium? 2 times 10 to the negative 4 molar. And what's the concentration of fluoride? We have CaF2. Okay, so we have CaF2. So it's going to be 4.0 times 10 to the negative 4 molar. Okay, this is a 1 calcium to 2 fluoride ratio. For this system here, would we write the precipitation equation or the solubility equilibrium equation? Have we precipitated anything?
No.
No, there's been no precipitate.
It's at equilibrium.
What? Yeah, but we didn't mix two things to get a precipitate. We write the precipitation equation when we mix two compounds to get a new compound, which is the precipitate. I would not call the CaF2 a precipitate, the solid. I would not call this a precipitate because it did not really precipitate. We just dissolved it to the point of equilibrium. That's why I tend to call that recrystallization when it turns back into the crystal. Okay. So would we write, in any problem where we're dealing with this kind of thing, would we write the precipitation equation or the solubility equilibrium equation? The C. So we're going to use the solubility equilibrium equation. Use this for dump and stir. Okay, so here's our solubility equilibrium equation. Where does the solid go? The solid goes on the left. Okay, there's our solid goes on the left. We are not going to use the PE. We're going to use the solubility equilibrium equation, not the precipitation equation. Okay, we good? Excellent. Okay. Definition 2 of a saturated solution. Remember, definition 1, we said it's a solution that contains the maximum amount of dissolved solutes. Second definition for saturated solution, a solution in which a dissolved substance is in equilibrium with some undissolved substance. This is going to take care of a situation where we mix two things and get a precipitate. Okay? So I might have mixed, for example, here. So this is, let me restart that. We're going to look at method 2 of making a saturated solution. So this is what I call mix and match. So you mix two compounds. And you match two of the ions. And they make a new compound. And that new compound is the precipitate. So two of the ions match together and make a precipitate. You can get to a maximum concentration of ions in a couple of different ways. You could do your dump and stir, but what if I had a solution that had just a tiny bit of fluoride in it? Let's say I had a solution that had a tiny bit of fluoride in it, say sodium fluoride. Could I add enough calcium nitrate to make the fluoride precipitate? Could I add an excess of calcium? Yes. Otherwise, that quiz you wrote wouldn't work, would it? Right? Would I have more fluoride? If I started with a tiny amount of fluoride and I added lots of calcium, would I have more fluoride than I have calcium, or would I have more calcium than I have fluoride? I'd have more calcium, even though these react in a 2-to-1 fashion. That does not mean there will be twice as much fluoride as there is calcium, right? Because I'm putting them in from different sources. The calcium's coming from one place, the fluoride's coming from a different place. So let's take a look at how this works. Once you get your precipitate, you will still have a small amount of dissolved ions in the solution. These ions will be at their maximum concentrations. It should say concentrations because they'll probably be different since the solution is saturated, but they do not need to be present in proportion to the coefficients. Don't worry, we're going to show you. That's what all these diagrams are here for, okay? So we are going to create a saturated solution of AgCl. We're going to do that one because the ratio is 1:1. The math is easy. Yes? So we took some original solutions and we got our chloride ions by using sodium chloride. So for every 1 sodium, there's 1 chloride. We get our silver ions from silver nitrate. So for every 1 silver, this is wrong, there is 1 nitrate. Fixed. Now, here in situation A, if you go and you count all the sodiums, there are 8 sodiums and 8 chlorides. But I mix up a different solution of silver nitrate and I don't make it as concentrated. So I only put in 5 silvers and 5 nitrates. Yes? And now I take those 2 solutions and I mix them together. Two of those ions match together. The silver matches with the chloride and we get an AgCl solid precipitate. That's our match. AgCl solid. How many chlorides are left in solution? 1, 2, 3, 4. How many silvers are left in solution? Just 1. So we have 4 Cl minus left over. And we have 1 Ag plus left over. And before you say, hey, shouldn't the silver be all used up? Remember that we do have a tiny amount dissolved because it's low solubility, not insoluble. Okay? This is really just here because we're low solubility. Now, could we write a KSP for this? First of all, what would be our solubility equilibrium equation? What compound would we be writing the solubility equilibrium equation for? AgCl. So where do I put the solid? On the left, AgCl solid. And on the right, we've got our dissolved ions, Ag plus and Cl minus. And my concentration here, the concentration of silver is 1. Okay, 1. We'll call it 1 molar. Okay, it's not 1 molar, but let's just make it a unit we can work with. Okay, what is our concentration of chloride? 4 molar. So what is our KSP value here? KSP is equal to, what is our expression? Silver times chloride, which is 1 times 4, which is 4. Okay. Now, what happened was 4 Ag pluses reacted with 4 Cl minus. Yes? That was a 1-to-1 ratio. Yeah? That was a 1-to-1 reaction. Is the leftover 1-to-1? No. So we have a 1-to-1 reaction, but the leftover is not 1-to-1. So when you plug those in, don't just be thinking, oh, I have 1 molar silver, I must have 1 molar chloride, because I know they are 1-to-1, because they did not come from the same place. I put more chloride in than I put in silver. Does that make sense? If I put in more of one, it's not going to be the same as the other. Okay. Next one. Are you following? Okay, good. Okay. Next one. Here we have, oh, and I've done something maybe not so clever here. I've put the same amount of things. I've made the solutions the same volume. I've made the solutions the same concentration. So here, this time I have 6 chlorides and I have 6 silver. And so when I react them, they still react 1-to-1. Okay, so they react 1-to-1. And I end up with 2 chlorides left over and 2 silvers left over. Is this one-to-one ratio? This one here. Or 2-to-2 ratio. And I'm going to use the same word I used in my morning class, preordained, which is a weird word to use. Okay? In other words, does it have to be that way? Or is it just coincidence because of the concentrations that I put together? Yeah. So is it preordained? Or is it just happenstance? And the answer is no, it is not preordained. It's just because I happen to use the same number of moles, I ended up with the same number of moles left over. Yes? And most likely, anytime you do this mix and match where you get the silver from silver nitrate, you get a chloride from a different compound, it's very unlikely that your two concentrations will be the same. It's very unlikely that they will be proportional to the coefficients. Okay, so when you mix and match, it is much more likely to end up with coefficients that are not proportional to the coefficients. So let's just show our KSP just to prove a couple of things here. So we already did our KSP for this one. KSP is the silver times the chloride. That's 1 times 4, which is 4. Is what he's saying making sense? Yeah? Okay. Now, here we had 2 silvers and we had 2 chlorides. Remember, that's just because I happened to put in exactly the right amount of each. How likely is it that I'll be able to get those amounts exactly the same? Not very likely. Unlike if I was to take silver chloride, AgCl, and I dumped it into water, would I get 1-to-1? Yes, because every time, if it was silver chloride, every time I dissolve a silver, a chloride also dissolves. Okay. So this is also 4. So what do we notice about our KSP value? It is the same. Why is it the same? Because it is a K is a constant. So remember, KEQ or KSP is always constant unless you change the, do you remember what can change the K value? Temperature. Remember, in an equilibrium, do concentrations have to or not have to be equal? Concentrations, do they have to be equal or do they not have to be equal? They do not have to. be equal. So if you form a solubility equilibrium by mixing two different solutions, this is a mix and match type problem. The ion concentrations will not be in proportion to the coefficients. So this would be, for example, mix AgNO3 and NaCl to get AgCl solid. On the other hand, if you start with a single solid, so for example, if you started with if you take some AgCl solid and you dump it into solution and stir, then you are going to get the ion concentrations will be proportional to the coefficients.
Say one more time what we were the second one. Even the concentration of ion.
Yeah.
So that depends on.
So that depends on which method you've done. Okay? If you've done a dump and stir,
Oh, I see. It also depends on the filter.
yeah. But yeah, it absolutely depends on the coefficients. I was just being oversimplifying there.
Yeah.
Yeah. Now, you get the same solubility equilibrium equation in either event, but if it is dump and stir, it's going to be 1-to-1, and if it is not dump and stir, then it's going to be X to Y, and we just don't know. Mix and match, that's going to be X to Y, and we don't know what those are. We would have to do some dilution calculations. Okay, I think that takes us to the end of this one. We're not done. I know. Dear God, trust me, I want to be done too. No, I don't want to teach it. Do you want me to teach it slower? Okay, I can go slower. I can tell you about my brother and the puppies he's looking after. So this is my brother. This is my brother who believes the earth is flat. Okay, this is my brother who did too many drugs when he was in his early 20s. This is my brother who hit his head on the ice when he was like a small child, and maybe that did some damage. We don't know. Well, maybe when you're a little kid they do, or maybe it was the drugs, or maybe it's just the way his brain developed. He has serious ADHD that is untreated. And he's never learned to manage it. So he has a hard time with the world. Yes? I love him, but he just does not function in the same reality that I do. Anyway, his girlfriend has a dog. Chongo. Chongo is the name of the dog. Chongo has sired 2 litters of puppies. There are 9 puppies in total. Okay, different mothers. Okay, Chongo's been a busy boy. Okay. Now, his girlfriend has left town. No, my brother's girlfriend. My brother's girlfriend has left town with Chongo and has left these puppies Yes. My brother is looking after 3 of them at my parents' house. My parents do not, like, he lives in my parents' basement because he is unable to look after himself in terms of like finances, right? So like whatever. But yeah, so he's looking after 3 of the puppies in my parents' house. My parents are adamant that they will not have dogs in their house. They have owned a dog. They are done with dogs. This is not their life path anymore. I believe at the age of 82, that is, and in their own home that they own and they support my brother, I believe that is their right. That is a boundary that they are absolutely entitled to set. No dogs. We are done with dogs. We are at a different stage of our life. We are not dealing with dogs, certainly not 3 puppies. Well, the 3 puppies are there. And so my brother is trying to find homes for them. They are random breed. We don't know what they are. Chongo has some greyhound in him, but he's sort of more stocky than a greyhound. The mothers, we don't know. There's some kind of hound. We don't know. But my mom really does not want the dogs. And so I go out I dropped some salads off at my parents' house because I get these salads delivered. They're delicious. Anyway, doesn't really matter. I go out into the front and the puppies are there and they are so damn cute. Oh my God, so adorable. If you want to see pictures, I have some on my phone. I can show you later. They are so cute and there's 3 of them. And I am just like all over the puppies. I'm like, And my brother gets like in this huge state because he's like, you don't even say hi to me. You're just all over the puppies. His mom brought you here to deal with the puppies. Have you had like a summit to deal with the puppies? And I'm like, no, I was just delivering salads and I didn't pay you any attention because you're not as cute as 3 puppies. So anyway, he's having like a hissy fit. And the dogs, he apparently has found homes for those 3, but he needs another home for the other 6. I don't know. It's just a big mess. Oh. And I thought I might try and help him find homes for them, but now I'm like, I am staying out of that. That is not my circus, not my monkeys. No. Anyway, staying out of it, staying out of it, staying out of it. Oh boy. Yeah, Chongo's owner should be finding, yes. But she's left. She's gone elsewhere. Anyway, let's go back here. We're going to do one more page now that we've talked about puppies. Yeah. Oh no. What's the time code? Oh, except for it's too late. It's too late to give the time code. I would have had to give the time code at the beginning. It's okay. All right. So we are now on page 35. Page 34 is going to be your homework. There are 2 definitions for solubility. Solubility can be defined as the maximum amount of solute in a given volume of solution. Yes? Now, you can also define it as the concentration of a saturated solution. These 2 definitions mean exactly the same thing, because if we take maximum amount of solute and we put it in a given volume of solution, what color do we get if we mix yellow and blue? Maximum amount in a given volume is the concentration. Yes? So the amount of solute, actually not maximum amount. Come back. the amount of solute, and the given volume gives us the concentration. The maximum a saturated solution has the maximum concentration. So do you see how those two definitions are actually exactly the same? No? Yes? Yes? Okay. So maximum amount of solute gives us a saturated solution. The amount of solute in a given volume gives us the concentration. Using this information, what are some units of solubility? Molar. What else? How could we write molar a different way? Moles per liter. Good. Are there some other ways to get an amount in a given volume? Grams per liter. Or we could do grams per milliliter. Or we could do milligrams per liter, or etc. Kilograms per meter cubed. You could actually do parts per million, things like that too, but we'll leave that. Now, in grade 12, we will almost exclusively use the molar solubility. What do you imagine the unit for molar solubility is?
Over liters.
Moles over liters. Molar.
Oh, boy.
So hard. Now, on page 4 of your data booklet, if we go up to the top, do you see how soluble means more than 1 mole per liter? More than 0.1. More than 0.1. Yes? That is an arbitrary decision. Okay? In fact, when the AP students used to have to memorize the solubility rules, their definition of soluble was you can form at least a 0.01 molar solution. So the what's the word I'm looking for? The number that you could allow that would be defined as soluble was 10 times lower. Okay? But here it's 0.1 molar. That's what we define as soluble in chemistry 12. So anything below is low solubility. Anything below 0.1 molar is low solubility. Anything above 0.1 molar or at 0.1 molar is soluble. And those numbers are going to become important because you're often going to see a question phrased like this. Does a precipitate form when we mix equal volumes of 0.2 molar and 0.2 molar? What happens to solutions when we mix them? What do they do to one another? We might get a precipitate, double replacement. What has happened to the volume when we mix them? The volume has gotten bigger. So what has happened to all the concentrations? The volume got bigger, the concentrations get lower. We call that process where we make the volume bigger, dilution, okay? These two solutions dilute one another. So let's look at our first solution. What is the concentration of silver in 0.2 moles of silver nitrate in 1 liter? What is the concentration of silver? 0.2 molar. Okay, I'm going to forget about my 0. That's irrelevant. All right, now we also have 0.2 moles of NaCl in 1 liter. What is the concentration of chloride? 2.
Sorry, 0.2.
0.2 molar. Now we are going to mix these. What is our new volume?
2.
Our new volume is 2 liters. And what were our moles? Have our moles changed? No, we still have 0.2 moles, and we still have 0.2 moles. If we have 0.2 moles in 2 liters, what is our concentration? Would it matter if I used 350 milliliters and 350 milliliters instead of 1 liter and 1 liter? No, because they're still, the volume is being doubled. The concentration gets halved. I could use 15 milliliters and 15 milliliters. Volume gets doubled, concentration gets halved. What are the ion concentrations now? Does this number look familiar or special?
That's the solubility.
This is the solubility boundary, yes?
What if I added more moles? Sorry.
We have like 1 minute left.
Sorry.
It's okay. Don't worry. Normally I love your questions. Okay? That's our solubility boundary. So anytime you take 0.2 and 0.2 in equal volumes and you mix them, it means you can use page 4 to predict whether a precipitate will form or not. Okay? Yeah. If I was mixing equal volumes of 0.1 and 0.1, could I use page 4? No, because maybe I could make that, maybe I couldn't. I just don't know. We would have to do more math. Your homework is page 34. Thank you for being a wonderful class. And we all made it through this afternoon together. Oh, the story about Chongo? Okay, so Chongo, here, let me turn off the recording. No, you want this recorded? Okay. Oh my God, my brother can never find it though. He would like flip out if he knew.